Bob Lucchese. It's electron molecule scattering calculations with grid-based methods.
All right. So first I wanted to say that I was a long time at Texas A&M, but now I'm permanently at LBNL, and this is the view outside the building 2 where I'm located. It's a pleasant place to work. Okay, so what I'm going to talk about is something fairly simple, but it's also the product of a small development group, right? It's myself, maybe one postdoc or whatever. So some of the issues that we tried to address with rather limited manpower. Okay, so why would be interested in grid-based methods? So we talked, Fernando talked about mixing hybrid Gaussians in the inner region and B-splines in the outer region, and one of the reasons why they've gone to B-splines from the outer region is that they're really a numerical basis set that you can converge fairly easily. But doing the whole electron scattering problem on a grid actually it allows you to smoothly converge the answer, go to higher partial waves, you make the radial density higher, and you can converge the answer. Whether or not it converges quickly enough, that's another issue. But it provides a direct, a simple way to converge the answer relative to how you're treating the one electron problem. And this really provides a very simple interface for the non-expert user. They really can. I've distributed my code some, and it's doing simple calculations, Hartree-Fock type calculations, but it's really quite easy to use, and there are very few things you can fiddle with. Once you have the quantum chemistry, the orbitals you're going to use to represent the target, then the scattering part, there's not much to do. You don't have to worry about any extra basis sets or whatever. The other advantage of a grid method is that you can easily go to high kinetic energy and you can go to high momentum. So if you want to calculate an electron that's got 500 eV of energy, that means you have to go to fairly high angular momentum, in the target, around the target. Also, in principle, the decomposition into different parallel sections is pretty simple. When you have a grid, if everything's represented on a grid, then you can distribute different parts of the grid to different processors. And at some level, this is a more simple to parallelize than a basic set base method. Okay, so I'll talk a little about a few of the things that we had to do to make the grid methods work well. So basically, the simplest version would just be a single center expansion. So you write every three-dimensional object in terms of some angular functions for harmonics and radial functions. For fairly small molecules, to converge the straightforward single center, well, this probably isn't converged, but to get a useful answer, maybe you need L max equal 120 in the inner region, describe where the nuclear cusps are. But once you've made this expansion, then all three-dimensional integrals then just reduce to some quadrature, a sum of quadratures in one dimension. Okay, so one thing that you might think about then is how to do the like two electron intervals. So in a spherical a grid, basically then what you're left with to calculate the 1 over R12 is you have these integrals of R plus or greater than. Okay, now quite a while ago we discovered, okay, well, what quadrature formula you're going to use to do this, and because of the discontinuity in slope here, you don't want to use a quadrature formula that goes over that discontinuity. So you have to derive special weights different weight to end at each different point that you want to stop the integral. Once you split it up to 0 to R and R, this should be R to infinity, sorry. You have to have special weights. So obviously if you're using like finite element DVR, you have to have a special formulas to go through each point in your element. Or I also used Simpson's rule, 8-point grids, and so you derive formulas depending on where you're going to stop your integration at each point along the grid. So that was one thing.
I think all the Newton codes formulas have similar.
No, the Newton codes don't, because they assume that the integral goes for the, up to 8th order.
But you can stop at any point along the way if you change the weights. I know this. Go ahead.
If you change the weights, yeah. But they aren't the strictly Newton codes weights. Okay, the other thing that, for sort of the most straightforward way of approaching this problem is, so let's say I want to take a product, take two orbitals, I want to get the partial wave expansion of a product, two orbitals, and I know the partial wave expansion of each term here. Well, you can derive what that is in terms of McClellan-Gordon coefficients, and if you look at this in the most straightforward way, you say, okay, I've got something like L squared terms here, L squared terms there, and I need to compute L squared terms like goes like L to the sixth. Okay, but that's not that, there's other ways of getting around it. This is including the spectral to spatial to spectral transformations. Basically, the idea is if you know the function, say GLM, if you know it in the spectral representation, partial wave representation, of course you can easily compute it in the grid representation. If you do the same to F, then each of those steps just goes like L squared terms, then this product is just also an L squared like term. Then the transformation back, if you do it one angle at a time, you like transform over phi and transform over theta, then you can accomplish this in L cubed rather than L to the sixth. And so that was a big improvement, it was a long time ago, 20 years ago, to allow the single center expansion really to be pushed to these very high partial waves. Okay, so based on this simple single center expansion idea, we developed a number of years ago, I think Fernando showed some results on O2 or one of those systems, where you can do linear molecules, you can represent your states using configuration state functions, maybe up to 10,000 or so, and you can include a number of coupled channels. So it's a close coupling expansion with correlated targets. Okay, for polyatomic systems, we have a general code which is only doing single configuration type wave functions, Hartree-Fock, frozen Hartree-Fock or something like that. But it can do 20 atoms, single channel, and it's easily parallelized, and we've distributed this up to a number of groups who are using it basically as a black box. Yeah, okay. So, but then it was always a problem of how, this was fairly difficult, computationally time, it was fairly slow, and we wanted to go to treat, correlated targets and whatever, as you see there, that's important. And so currently we're spending some time developing a grid-based method based on the complex cone method, which the people at LBL had developed. So it's going to be based on the polyscat, which is this general polyatomic Hartree-Fock code. And instead of using the straightforward single center expansion, we're using something called overset grids. So I'll explain those a little bit. Okay, so the basic problem, of course, with the single center expansion was the fact that, for example, the interaction with the nucleus, if you expand it in partial waves, L equals 0, and 5, 10, 20, whatever, that the singularity at the nucleus basically doesn't go away as you go to higher and higher L, right? So you really can't converge these very well. I mean, you can push at some point, you can extrapolate, things you can do, but you can't really converge the calculation in partial waves because of the off-center nuclei and corresponding cusps in the wave function. So the idea that we're playing with now is to use something called overset grid. So basically, we have one encompassing grid, which is a spherical polar radial grid, but then around each nucleus we put a little subgrid. And the idea is that around a given nucleus, then we have a spherical polar radial kind of grid, and then we combine the information from the overgrid and the little subgrids. And so we use a very small partial wave expansion around each subgrid, maybe L equal 4 or 5 or something like this. And the central grid has to be a high enough partial wave so that you can actually, successfully connect between what's going on in here and then what's happening outside here. All right, so the essential piece of this is how do you decompose a function defined in 3 dimensions to something that's defined on these various grids and subgrids. So basically you have to define some sort of switching function, and we use something that's based upon the Becky type switching functions that we use in DFT. And so the idea is that if you can decompose the spatial wave function in terms of different centers, then you can write the effect of some operator on your 3-dimensional function as the effect of that operator operating on these spherical subgrids, and then you just have to add them back together again. The main, and this kind of thing works for the exchange integrals, or as you'll see, we use free particle Green's functions, and you can apply the same idea. But basically the point though is, one of the limitations is that once you've gotten to this point, you have a function defined from each center, but then you have to re-expand it back to all the other centers. So if there's overlap between the grids, depending on what function you're looking at, you have to do some kind of interpolation of the function that you computed from a particular subgrid, and you have to interpolate it onto the points that weren't on that subgrid but were defined on the overgrid. So the interpolation actually turned out to be a little bit of a problem. Okay, so basically the idea is we define then this grid. It's over complete, but it's a large grid which is fairly efficiently localize the nuclear cusps and the potentials, and so basically you can then, so we're going to solve the transition amplitude or the T matrix or the foot dipole matrix elements using a variational expression based on, in this case we use the complex cone variational expression. And so the idea, if you look at this and you think these phe's then are just some grid-based functions, well, if you didn't know anything about what you're solving, you're trying to invert some E minus H defined on some big numerical grid. So you might say, okay, well, default thing would be do some kind of Krylov iteration. And so a typical Krylov iteration would be some initial guess, E minus H to some high power. This doesn't actually converge very well for this problem, and so the idea is we have to then come up with a better iterative scheme. And lo and behold, the thing that worked out really quite well is to do something that looks like the Schwinger method, which is what I've been using previously, which basically you have a free particle Green's function and then the rest of the Hamiltonian. So if you do the iterates,
No.
Yeah. So this probably should be a power, but anyway. So basically, once you define your functions are going to solve this linear algebra problem on this way, then E minus H, which you need for the cone method, then just comes out to V minus VGV onto this thing where I've taken away 1K minus 1. One of these GV terms. So writing your variational basis set in this fashion, you obviously get the right boundary conditions because you have the Green's function there, and you can show that with this basis set you basically have NN Hade approximates to the final T matrix. So it's a rapidly convergent way of solving this problem. So using the standard Krylov method based on E minus H operated repeatedly, this very simple model problem, it took something like 40 iterations before it started getting close to the right answer. Where using this Born-Arnoldi scheme based on the GV iterates, in 5 iterations you get the right answer. Okay. And the different curves here, n equal 15 was a lower order how many? 5, okay. A low order FEM DVR, 15th order, 24th order. It converges even up to fairly high. Okay, so we can apply this then. We applied this to a number of things at the sort of static exchange level. And so here we're comparing the traditional single center expansion code. And by the time you get to 100 for CF4, it's really not quite a converge, where the overset grids with L equals 35 is pretty well converged. And this is all headed down to where the solid red line is. And the scaling of the partial wave expansion you need in the overset grid The whole problem still scales to L cubed, but you don't need to go nearly as high in partial waves as you do for the unconverged single-center expansion. Okay. So as a small operation, let's say, there are some things that I would have found very useful in developing some of these codes. So one would be like, is there some simple parser that you can take input? Like if you look at like Moltro, there's certain sort of input language it has, and obviously they have a little code there that parses those and drives the program. Do we need to go to use Python as our interface, which is actually sort of complicated in terms of ways you can use it, but okay, you could do that. Or you could have just a simple, here's data, here are commands, here's a loop. That's all you need. You don't need the full power of Python. So something like that would have been useful. Obviously, having well-established reference test cases. I was talking to Roger Bayo, who has been a student of Fernando's. He's saying, well, there was some effort to find out, what the time-dependent response of the hydrogen atom is to a given field. And people can test their propagators and whatever, and to have that kind of data or data sets available, people could test their programs. Would be useful. Something like N2 and N2 plus. If you start sharing libraries, you need to have extensive unit testing, so if you start modifying things, you haven't messed it up or whatever it is. But also, again, Fernando described how the time they spent trying to dig into Molpro or Molcast, or whatever it was. Some simple things. Could, for all these different quantum chemistry codes, could there be a standard way of getting basis sets and orbitals into your code, or density matrices, or whatever it is? Just some standard references. And then, are there standard data structures like we use libint for some of our molecular orbital or the Gaussian integrals. Should we come up with standards for how to pass that information from one part of the program to another? Okay, so single-center grids provide uniform but slowly convergent. Oversight grids, you can converge them, to 10 to the minus 8 or whatever it is you want to the right answer. So they're quite useful that way. We're working on including correlation to the grid complex cone. And this ePolyscat, I have a little experience with distributing, and we'll probably do the same with the complex cone. What do you got? So the current DOE fund me is there. I did LBML. I'm collaborating with Bill and Tom. Lauren Greenwood is a postdoc, is now a faculty member at Kansas State. And earlier, of course, I was a graduate student with Vincent Coy, and some of this work started back then. And then the ePolyscat came from a semester I spent in Rome with Franco Gianturco. Thank you for your attention.